amazement at this program in front of me here. This is a program called WebMO. Okay, so myself, like many teachers, and I'm sure students around the planet, have been trawling through databases, pages and pages of SDBS and Chem Spider and NIST, trying to harvest a research question from a quite narrow field of data. Okay, we are limited, I know, by a number of research questions which keep coming up again and again. And just to reiterate, it isn't what you do, it is the way that you do it which will get you the marks. I then attended this training webinar, very grateful to Jon Chui, much appreciated John, the legend, last weekend. And I watched in awe and saw my jaw drop as I realized that this should have been the way I've been going all along. So, when you want to log on to, I need to change my password. When you want to log on to WebMO, all you have to do is put guest, G-U-E-S-T, guest, G-U-E-S-T for the password. Okay. It is free. There is no money changed hands. You're not expected to make any contributions whatsoever, which is always a good thing. When you land, you will land at this page. Okay, I assume that the number on the left is a sequential, yes it is, sequential number assigned to each job. This will become clear as we go on. The name of the molecule is up to the person. You could name your molecule your name, that's perfectly fine. The description, we'll go through that shortly, and then you can see statuses and the time it took to complete. Clearly, in the last 20 or so iterations, there have been 1, 2, 3, 4, 5 failures on screen. The failures, I believe, are because they've gone beyond a time limit. Okay, so first note of caution, if the processing takes longer than 30 seconds on the computer which is doing the number crunching, your job will automatically be killed. Okay, there is a workaround for that, but we'll save that for the next video when I get around to doing that. So, without further ado, let's have a quick look. We're going to go to New Job, and we're going to create New Job. Okay. What does this software do? This software uses molecular orbital theory, and it calculates bond energies, bond enthalpies, bond orders, hybridization, energies, strain energy, which is a summation of the torsional and the steric contributions to the overall energy of the molecule. More of that later. So let's have a quick look. You land at this screen, and there's a big refreshing white piece of screen in front of you. So here on the left, we'll just go through the buttons. Top button is to build a molecule. Okay, so if you want to build, you click that. Next one is your periodic table. It defaults to carbon because this is for building primarily aimed at organic chemists, but you can use any element in the periodic table, and they are all beautifully named there before your very eyes. We'll come to that shortly. This one allows you to twist, I believe, your molecule. This one obviously zoom in. This is the select button, or adjust, sorry, this is the adjust button, and we'll be using that very shortly. We can change the adjustments. We can clean up geometry. Don't worry, we'll come to that. We can also fix the molecule mechanically. Beautiful. Can symmetrize. Remember that VESPA stuff? The VESPA, this is, you know, this package, I would say, is fantastic for bonding, periodicity, energetics. You can even bring in equilibria, definitely organic chemistry, and certainly there will be a nod to internal assessment as we go through the guided tour here. We have Huckel orbitals, whatever they happen to be. There's a beautifully that a DZ squared that I can see there. You can undo and redo, which I find myself using quite a lot as I'm going through this software. Okay, it is kind of intuitive. We get used to it, I think, is fair to say. So, where are we? Let's have, is that carbon? It is. Let's pick oxygen. Okay, so I'm going to build. So if I click on the screen, there before me is a nice rosy red oxygen atom. Now, I could click here, and clearly there is another oxygen atom. But they're not bonded, so how do I bond them? Well, I hold, I drag, and I drop, and there is a OO single bond oxygen molecule. We all know it's got a double bond. So I drag and drop from one of the atoms to the other atom to make it an oxygen doubly bonded molecule on the screen. Okay, so let's just undo that and show you how easy it is. Let's have some carbon. So again, I can click, one carbon goes on the screen, drag and drop, drag and drop, drag and drop. Get the idea. And let's make that one. If you somehow go before the carbon atom, it will still hover in space. It will only do what you tell it to do. Okay, let's build some benzene, shall we? Put some benzene in here. My drawing on here is massively better than my drawing on the whiteboard at school. Now you're looking the same as me and thinking, well, that bond's really short, that one's really long, the geometry's all wrong, it doesn't look like benzene, right? So let's have a look at the top and see what we can do. There's a cleanup button. Okay, we don't draw hydrogens, do we? We're chemists, we're kind of lazy people. So I click add hydrogens, and I've added my hydrogens. I can click this button here, and I can give it a spin round in space. Look at that beautiful planar molecule there. I could click on this carbon. Can I do that? Oh, let's do it. Clean up. First things first. We've added hydrogens. We can do the hybridization. We could have a look at that. We can do the geometry. Oh, now we're talking. We've cleaned up the geometry. And the buttons which we were guided to use during the webinar was clean up either idealized comprehensive or mechanics comprehensive. Okay, so it is important that you clean up the geometry before you send it to start doing jobs. As I've played with this software, I've realized that when I go into lookup, I can import molecules from those packages. There's a databases button, and I saw that and I was like, oh my gosh, that's all the things which we've been independently trawling through to gather data for our internal assessments. So I've just drawn what I hope is benzene. Let's have a click on Chem Spider and see what Chem Spider gives us. And this is the beautiful part of it. So here is benzene. I've got the isotopic mass, the average mass, and clearly as we go through, we will hopefully have some spectra. I've got the infrared spectra here. We've got the UV spectra here, and I'm sure with a bit of digging we could find the NMR spectra as well. So that's good, isn't it? Why is that good? Well, you're all thinking like me, aren't you? You're all thinking, what if I change that fluorine? What happens to the NMR spectrum? Or that hydrogen for fluorine? Or maybe if I put 2 fluorines, or 3, and so on, and so forth. And then all you do is look up, goes to the database. Let's have a look at SDBS Spectral Database. That's one of my many used databases for recommendations. Don't forget, on SDBS, you do have to agree to the disclaimer, and then it will take you in and hopefully drop you onto the page. Okay, so you have to write it in. So you can type benzene in, you can get your carbon 13 or your proton NMR spectra there. But back to the molecule building thing. So playing with this is great. So you can put on that tool, you can look down the molecule. Let's start a new one, shall we? Let's have another one. Let's go back to default on carbon, drag, drop, carbon, drag, drop, drag, drop, drag, drop. So we made a butane back chain, or let's make it pentane, just for a laugh. There's pentane. What we're going to do now, we are going to calculate, we're going to clean up, we're going to add our hydrogens. Look at that, play for hours with this thing. Comprehensive, idealized, now look at that. Is that beautiful? I think it's beautiful. We can use our adjust tool here. Notice when I click an atom, so maybe I went a bit quick there, this arrow here click it, and then click an atom, click any atom, and then at the bottom it will tell you the hybridization, which is sp3 clearly, and the charge. Oh, that's great, isn't it? Why is that great? Because you can, as you are teaching or as you are learning, you can stick in a double bond now, okay, and you can say, well, what's the hybridization now around here? Oh, good, jumped one ahead. So now we've gone sp3. Oh, it's not recognized it for some reason. It should be sp. It's because we've deleted. We've lost a bond. There we go. That's better. 1, 2, 3. I've got a pentavalent carbon atom. Missed it, honestly. So there we go. That should be saying sp2 now, shouldn't it? It's still saying sp3. Why is that? Maybe I need to refresh. Anyway. No, that's fine. If we give it 2 clicks, it gives me the bond length. What do I mean by 2 clicks? Let's do that again. So I've got my pointer tool. I'm hitting my terminal carbon atom. Still an sp3. I'm hitting my second carbon atom. It's telling me the bond length is 1.54 angstroms. Angstroms, international unit. You don't need to worry about it. It's a numerical value. Learn it to deal with it. Move on with your lives. So I hit 1 and I get the hybridization. I hit 2 and I get the bond length. I hit 3 and I get the bond angle. And reassuringly, we are looking at 109.5, which must be clearly around this one, because we know that this one is going to be 120, isn't it? Yes, Mr. Mitchell. So there, we've got the hybridization, got the bond length, hybridization, bond length, and third one is the bond angle. So what happens if we click 4? 4, we get this thing called the dihedral angle. Now, the dihedral angle, look at that beautiful thing. You're teaching your eclipsed and gauche conformations. This is just a blessing of a tool that you can play with. So a dihedral angle is in relation to planes of symmetry that you're looking at with your molecule. Here is 1, 2, 3, 4. There is butane. And as butane rotates around that sigma bond on the central carbon-carbon atom, we're going through our Gaussian eclipsed trans and is that ans? Opposite rotation, and the steric interaction between the ends of the molecule, the hydrogen and the methyl hydrogen. I'm assuming that the biggest delta G on there, which is that 18.4? Yeah. That must be where the 2 methyl groups, I'm guessing, are interacting. Okay. We have that discussed at the bottom on the diagrams. So you can build molecules within the software within here, and you can get the dihedral angle. Well, why would you want to do that? Well, you can change it. Okay, so let's go to my select tool. Let's start with a new one. Let's go to a new one. Periodic table, carbon atom. Let's have carbon. Let's have some ethane. So I'm going to add my hydrogens, comprehensive idealized, give it a spin because it's fantastic to do. Look at that. Wowzers. Beautiful. And I'm going to have a look at the bond length. So I'm going to use my tool, click this carbon, 1.54 angstroms. Beautiful. What if I want to change that? Oh, I can change the bond length. Let's make it 1 angstrom. Oh, it shrunk together. Why would I do that? Well, I can change the bond angle to be whatever I want it to be, I believe. There you go. Look at that. Oops. You get used to clicking the buttons on the left hand side and going back. You can barely, it's totally eclipsed the other carbon atom. Now looks like an octahedral complex, doesn't it? So that's really small. Let's change that back. So where was it? Tools, adjust, and I need to highlight it first. See, I've only been doing this a week. I'm not claiming to be an expert in, as you can tell, in any way, shape or form. I just thought that this was so powerful and so brilliant that I just had to get it out there. So anybody looking at May 21, and I'm looking at all the emails that I'm getting on a daily basis, and I'm struggling to answer them all. How do I do a database? Where's my research question? Where do I find the data? This comes at it from the other end. This is plotting molecules in and then generating data. So how do you generate some data? Hopefully you are used to using, or just have a play with this. I used it with my kids this week at school. They were very happily building molecules within, I don't know, 15 minutes, something like that. So there's oxygen. I'm going to clean it up. I'm going to optimize it. Because don't forget what we're talking about. Here is a bond between two atoms, and without going into too much detail, because I don't know how to, in all honesty, we're talking here about a harmonic oscillator, or a quantum harmonic oscillator, and in basic terms, that's all I could understand. We are talking about the point at which the two nuclei, positively charged nuclei, are at the perfect optimum distance, balanced by the electrons being shared in the middle. Any closer, the repulsive forces of the nuclei would push them apart, and any further apart, then they would start to lose the attraction with the electrons, and eventually that bond will break. So if you want to know about that, good old Chemistry Libretext has beautiful maths and descriptions on there. And if you're looking at oxygen and you're working out the bond energy, which I'll show you how to do very shortly, this is beautiful background, and this is certainly already an IA worthy exploration. So looking at I don't know, oxygen, the rest of the group, you can look at those. You can look at hydrogen halides, you could look at the halogens, you could look at substituted organics. As I was watching this, I was just like, oh my gosh, there's so many things we could do. So how do you do them? Okay, so hopefully now, it's probably a good time, just load up WebMO. It's guest again, get the periodic table up, build a molecule, have it going on the side of the screen. You can build water or hydrogen or oxygen, or just keep it simple. Remember the 30-second thing. If you do complicated molecules, it will stall and you won't get an output. So let's have a look. Now this is where it's a little less than intuitive. You go down to the bottom here and hit the blue forward arrow. Okay. We then get to choose our computational engine. Jon Chui, thanks again John, said always use games, I think it's from the Google Translate alert, it is Portuguese to English, and it's using this server. Don't change these, just leave it as it is, that's fine. We then go forwards on this arrow, and then you have the games job options. So the job name, this is oxygen, and I'll do Mr. M for Chem. I want to look at I don't want to look at the molecular energy. I've been using molecular energy. I've also been using optimizing vibrational frequency. Okay, I've not used the UV-Vis, NMR, molecular orbitals yet. It is there. I'm 1 week in. I just think you can achieve so much even with a few hours investment in terms of progress on teaching, learning, and internal assessment. John did guide us to use UHF, I believe, if memory serves me correctly. If that's incorrect, please shoot me down in the comments at the bottom. And use accurate on the basis set. Okay, so name it, molecular energy, UHF, and accurate. Okay, there are other things in here which I have not played with, and I don't pretend to understand them, so please don't ask me. There are lots of videos that are found on WebMO on YouTube as well. It's obviously used a lot in universities and for master's degrees and PhDs and all those things. And let's have a look. When we click the forward button, it goes into the queue, which was the landing page when you first came into this software. You can see lots of people are clearly using it. It has moved on since we looked 5 or 10 minutes ago, and then your job will appear at the top. It's complete, What's complete? Well, you've just taken up time on a server doing very, very advanced calculations of this ilk. Where are we? The ones that we were looking at. There we go. I will get prepared one day. Calculations like this, or the Schrödinger wave equation, if you want to have a look at that one. And it takes a lot of computing power to actually generate all of the data that you need. So we've completed oxygen, Mr. M for Chem. Actions here. Have a look at the file. So hopefully, fingers crossed, yes, the molecule has come up. And you sat thinking, but it looks exactly the same. All that's happened is there's a number 1 and a number 2. Okay, let's scroll down a little bit. Now, what we have underneath is an overview, first of all, of the UHF energy. Just think of that as the molecule's energy for now. The UHF relates to the mathematical transformation that it's using. It's a measure of the steric and bond energy contributions to the overall energy of the molecule. Okay. We've got the partial charges. Clearly there are no charges. It's a formal charge of 0 and 0 overall. But imagine if you've got F2O or you've got H2O, you will have different values down here, so you can use that. You've got the bond order. You've also got the molecular orbitals down here. Molecular orbitals are beyond International Baccalaureate, but at the top you can just press it. It does a little calculation which is currently running in the background, and then the kids love to, or my kids were enjoying very much seeing which orbital was where and playing with the molecule on the screen. Hopefully someone's thinking, wow, already, okay, as I was. Okay. So we've got the molecular orbitals and we've got the overall energy of the molecule. Now the energy of the molecule here, this is in something called Hartree units, and I'd never come across Hartree units before last weekend. They are 1 over 2,625, that's how many times I've done the calculation, of kilojoules per mole. So the conversion is, and conversion is one of these. So what we want to do is Hartree to kilojoules per mole, and there we go, 2625. I think I remember that one correctly. So a Hartree is a unit of energy used in molecular orbital calculations. We got that. A Hartree is equal to 2,625 kilojoules per mole. And now we're home and dry. 2,625 kilojoules per mole. That's so IB, right? That is the IB. That is beautiful. So I can build any molecule I want within the 30-second window, and I can get the energy of the molecule. That's already making me think of internal assessment possibilities that could be done, as well as teaching and learning possibilities in here. Now, if you're a teacher, great. Get onto my IB, and you will find the thread on the DP chemistry molecular modelling. This was the live stream which I watched Jon Chui do. And Jon has shared the interactive whiteboard, which is publicly shared. Thank you, Jon. And the collaborative Google Sheet. Now, what I was just looking at for oxygen here and getting the energy here, 149 point, that 10 decimal places, Hartree units. What Jon guided us to do was he set up a collaborative Google Sheet, which is just loading up now. His kids, the participants on the webinar were each given a bond length. Remember how you adjust, you click, get the bond length, it's at the bottom of the screen. Did the calculation to get the energy, so forward, change it to UHF, change it to advanced. Then they got the Hartree units, which were pasted into here. The calculation, 2625 to kilojoules per mole. And then he's done the difference between the ground state from the equilibrium position. And he got a beautiful Moore's curve and explained to us that this is the equilibrium position, which matches the one which I was just playing you, which is here. Look very similar for a very good reason, because they are looking at pretty much the same thing. Okay, and as a collaborative exercise, it was fantastic. In fact, I loved it so much that I did it with my kids at school, and we it's modeling. There we go. So last week at school, I got my kids, and as a classroom activity, it took one lesson, about 1 hour. It took them, as I said, 15-20 minutes to get their heads around the WebMO suite of activities, and then they just copied and pasted in, and these were the data which my kids generated during modeling 2021 during the lesson on Friday this week, so just yesterday. It's taken a little while to wake up because it's clearly running lots of things in the background today as I'm recording the video, but there we got exactly the same idea. And then I got thinking, well, if it works for hydrogen, it works for anything. And then I started looking at one that's going to be for oxygen, and we can look at the optimal bond length. You can just Google the bond length. The literature value is freely available on Google, and the conversion for Hartrees, and then the bond length of oxygen is 1.208 Armstrongs. So I get kids to go from, I don't know, 0.2 to 1.5 Armstrongs, maybe 2 Armstrongs as I've gone here. Get the energy from the software, paste it into here, and you'll end up with a beautiful curve. And you can look at this and go, well, here is infinite separation. So this is 2 hydrogen free radicals. This is with the hydrogen atom. And this is where the bond length should be. The relative energy is 0 relative to the rest. These are all higher energy than here. And it's somewhere between about 715 to 745, somewhere around there. And then you look at the Googleable bond length, and it's just about the same. And then John mentioned precision. Your precision is take this range of 0 values, get the mean from there, compare it with the literature value, which is just easily Googleable, and there you have your precision. There's your uncertainties. Protest. Beautiful. Okay. So, what I suggest you do is get calculating and have a look at what you can achieve. The more time I spend with it, the more I'm finding. We can find bond stretching, get the total energy for the molecule, which is in kilocalories per mole, straight conversion to kilojoules per mole. There's data processing for your IA. So what I wanted to do then was, because John has shared it in my IB, I suggest you have a look at that. On the sheet, he's also got another 2 different ideas which he uses. You feel free to, he shared it, so feel free to have a look at them. One's on the relative energies of SPD orbitals as you go across the periodic table. Smell an extended essay warming up there. And one's on the dihedral angle. You can get the dihedral angle, remember 4 clicks on that front screen, and that's freely available, so have a look at that when you've got the time. So this was just a quick throw up I wanted to do to show you the possibilities that are here. You are limited to the 30-second calculation, but that's not a problem. If you're doing small molecules, it's fine. So here you see on the left hand side what we did, and the 30-second. So let's do a new one. Let's do something. I'm going to have to start again, showing off my weak IT skills here. So let's build something a little bit more interesting and see what the software does with this. So it's guest again. Beautiful. Thank you very much indeed. Mine's still the first job. Oh, let's change my password. New job. Create new job. Should have run this as a live stream. Never mind. Periodic table. It is on carbon. Click. Drag drop. Drag drop. Drag drop. Drag drop. There's a very wobbly cyclobutane. So again, clean it up. idealized. Oh, look at that. Play for hours listening. And give it a spin around. Just look at that. More chair conformation. Look at that. Beautiful. Strain energy. That will just come up on here. That's again steric and bond energy summed. Van der Waals radius. Just look at this. From a place of very small data, with all of it's just an explosion of data that you can get with it. Don't forget, you can look at the databases. You can go straight to PubChem, ChemSpider, NIST, Sigma, NMR, ShiftDB, or the SDBS spectral database. You can calculate symmetry, obviously. Huckel electron density. Let's have a look at that. What's going on there? Look at that. It's just the business. That is beautiful. So this is obviously the probability clouds for distribution of electrons around cyclobutane. I am blown away. I am blown away. So if I wanted to look at the energy of that, remember, it is just click forward at the bottom. Games, bless. And calculation. Let's have a look at optimizing vibrational frequency. Let's go UHF. Again, I hope that's correct. Let's go accurate. So optimize vibrational frequency. UHF, accurate. See what happens. Will that complete within 30 seconds? We shall see. Clearly I'm running this live. Not too much preparation for this video, I'm afraid. But just look at it. Just wow. And even when you drop on this page, if you're a student, I would just encourage you to click on any of these files here, the completed ones, and just see what other people are building. Okay, you can spin them around. You can practice getting the bond length, the bond strength, the hybridization. You could challenge each other to a hybridization game and check it. You can build molecules and get the NMR spectra from SDBS. You can look at moving a functional group and seeing the result on the chemical shift on NMR. Again, this is just so open-ended. It's an absolute boon for anyone. Now that's taken 44 seconds. That means it's probably died a death. There is a workaround for this. Yes, it failed. So looks like we failed again. Okay, let's try something more simple then. Go back to here. It's all good practice. There's carbon, 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 carbon. Let's go straight chain butane. Clean up. Let's do idealized. And we'll go forward. Maybe it was because I selected the more funky calculation, which was optimizing vibrational frequency. Let's go UHF. Let's go accurate, because that's the sort of people we are, and see what happens now. So I've taken it from cyclobutane down to straight chain butane. So a simpler molecule, hopefully with easier calculations for the computer to run. The workaround is something called Chem Compute, which I'll do a future video on when I've got my head around it. I've not I've not cracked that one yet. I'm still only probably a page ahead of a very basic user on this one at the moment, as you can probably see. Okay, so here's my butane. Run, come on, fingers crossed, fingers crossed. You can do it. Still running, 33 seconds. It's not going to let me play. It's not going to let me play. No. I'll see it will probably say that it's got error. Yeah, failed job. It was a failed job. Okay. Well, it's still there. It's still there. Okay. And it's still giving my UHF energy, which is what I was after. RMS force, Google it. I have no idea. Dipole moment, as I mentioned before, that can be used. Substitution, what's the effect on the dipole moments, what's the effect on the chemical shift. Keep your IV to 1, DVs just expand beyond 1, 2, 3, 4, whatever you want. Make it feel like 10 hours. Look at this. This is internal assessment gold, absolute gold. You know, and I hope that in making this video, a few things happen. One is it alleviates some stress for teachers and kids when they see, when you play with this. After an hour, you'll be ahead of me easily. Okay. The possibilities are endless for what you can do with it. Keep pressing buttons. Don't worry about the 30 seconds. Get confident with the basic things like, I don't know, hydrogen halides, halogens, water, ammonia, just the basic IB molecules. Get familiar with those. have a look at them, substitute them, look at the effects, look at the bond angles, look at the hybridization, all that stuff. This is for me revolutionary, seriously revolutionary. This is going to change the whole map of how I actually teach chemistry, when I can put these things on the board and the computer is doing those fantastically advanced calculations I wouldn't have a hope in hell of doing, and yet I can play with them on the screen and show the kids just the beauty and the majesty of chemistry. Okay, I'm going to stop there. Just a quick video, few pointers. Go and have a go, have a play with it, see what you can get. Next video, we'll have a look at how we defeat the 30-second barrier when I've learnt how to use the next program. Okay guys, smash that subscribe button. Thank you very much for watching. Hope you enjoyed that. Big love, keep it real.